на Большом hadronном коллайдере. Здесь также присутствуют сотрудники этой лаборатории и, Саша, и комиссия... Комиссариата атомной энергии во Франции такой есть. Это Максим Китов и Сергей Барсук. Вот Сергей.
Да, я тоже из...
Комиссариата?
Нет.
Из Лава. Из Лава. Okay. Achille, now that is second visit in Kharkov.
Yes.
Поймете по-русски? Хорошо. Achille уже не первый раз в Харькове, когда у нас была зимняя школа CNRS здесь, он выступал с целым рядом докладов на этой школе, именно в этой лаборатории. Насколько я понимаю, обстановка тогда очень понравилась, и вот сегодня делегация снова к нам приехала. Achille, please.
I think I have to switch to English. Try. Добрый вечер. So, thanks to you for the kind invitation to give this seminar, and for me it's a pleasure to be here again. In fact, as Professor Shurga remember, I was here probably 4 or 5 years ago. In fact, in this room where we gave, there was a nice moment with the lectures with a lot of students, and so it's a pleasure for me to be here today. So today, the idea is to give you a flavor of some results from LHC, and so I prepared this seminar with Sergei Barsuk, which is actually working on LHCb experiment, and with Maxime Titov, which is in fact working on CMS experiment. So maybe I wanna just start from a very general introduction. I mean, 1 or 2 minutes, just by saying that of course we have 2 approaches, what I call exploration of 2 frontiers, so the way of trying to discover new phenomena, which I like to call it relativistic path and quantum path. Of course, is a bit a schematic point of view. Of course, when you do relativistic path, means that you just try to increase the center of mass energy in order to go and discover new particle. And in this case, I mean, the key issue, what is crucial is just to increase the center of mass energy. And okay, in LHC program, there are 2 topics, 2 experiments which have been, which is exploring that, which is our Atlas and CMS. On the other hand, as you well know, I mean, the history has shown that often discovery or hint of discovery came from precision measurements, and precision measurements is what I like to call a quantum path, in the sense that you know that of course when you have, of course here are real particle, but in the loops you have a virtual particle. Of course you know that inside these loops you can make circulating any kind of particle, so somehow many observable like branching ratio, rare decays, CP violation and so on can be very sensitive to the presence of a new particle inside these loops. And often, in fact, even a very, very heavy particle that often are not accessible by just direct observation. So the quantum path, the key word is precision. And when you say precision, means that you make precise measurement. And so the crucial word is to have a sort of luminosity And the quantum path in the LHC experiments is made by LHCb. So today I will discuss both, LHCb results, which are studying more flavor physics, and I show you also results from Atlas and CMS, where in fact will be centered my talk essentially on in this part on Higgs discovery. So now, okay, everybody know what I'm talking about. So LHC is the largest hadron collider, which is schematized here. A collider long 27 kilometers, 100 meter underground, nearby the Geneva Lake. And essentially, you know that you have 4 experiments. So I already told something about that, where the general purpose of Atlas and CNRS is more to study the origin of the mass and the new particle. Here is studying another way of approaching new physics by studying matter-antimatter asymmetry. So here I schematize here. So I apologize that I will not discuss, of course, another very interesting program where I know that there are experts here in the room, which is heavy ions, which there is a dedicated experiment in LHC, which is ALICE, which in general are studying general property of quark gluon fluid. But I mean, this will be not discussed in my talk. Of course, what we discuss here is essentially results from proton-proton collision at the center of mass energy between 7 and 8 eV. And then I will say a few words in future, because you know that in 2 years' time after the shutdown, LHC will be started about 14 TeV. So now very briefly, before going to the results, I mean LHC work, okay, here you see a plot which has been, that you probably are used to. LHC work rather impressively from, okay, this, you see that here, here we went up almost to 20 inverse femtobarn. Just to give you an idea, I mean about 1/4 of these were necessary to do Higgs discovery. So this is of course this is the only one of the few transparencies I show on machine. Just to tell you that LHC machine work very well after a start which was not probably fantastic, but this year really almost reached the nominal luminosity. So LHC was scheduled to run at 10 to the 34, and finally at the end work at 7 10 to the 33. So with a very high number of branches, and so really at the end was I mean up to here was really running at nominal condition. On the other hand, we know that this luminosity was far too big to be suffered by the other experiment, which is LHCb. So LHCb, in fact, they did the trick in order to decrease the luminosity at the LHCb region, interaction region. But what I want to show, then I will say a few words on that, but what I want to say here is even those LHCb work at constant luminosity, which was much higher than what was foreseen, so twice higher. And also this detector behaved quite well and managed to take data, and I will show impressive results from LHCb. Just to tell you a single word on that, this was quite a tricky way of reducing the luminosity in LHCb region, because otherwise the detector was unable to work with the precise measurement with such high luminosity. The idea was that, of course, you know that luminosity as a function of time normally goes down like that. This is a profile of luminosity in a function of time, for instance, for Atlas and CMS. And this is due just because the luminosity decrease as a function of time due to the loss of particle. And then, in fact, LHCb, you see that almost work at constant luminosity. And the idea was that the two beams were slightly displaced at interaction point of LHCb. And then this displacement was reduced a little bit when the luminosity were So in the sense that the luminosity was always constant at interaction point in LHCb. So this was a very good trick that from experimental and machine point of view was not completely evident to achieve, but was perfectly achieved by LHCb. So you see how constant was the luminosity on that with, again, the automatical correction of displacement of the two beam, one with respect to the other. So now with such a good luminosity and data, in fact the detector I will start to show LHCb, first saying a few words about detectors and then also showing results. Now, maybe in a slightly more pedagogical way, I want to say that what is B production? LHCb is the experiment to produce B meson, to do, B physics, so to study CKM matrix and study CP violation. So here, B mesons at proton-proton collision are produced essentially by flavor excitation or by gluon splitting. So the bar are coming from splitting of the gluon. And here is showing that, of course, about 40% of events are in a very small solid angle, and the B hadron momentum is about 100 GeV. Okay, this is very important because you know, that the path the B are traveling is given by beta gamma, the boost, which is order 100, 100 divided by 5, and the C tau, which is about 500 microns. So you have a flight distance, which the B's are flight distance of the order of centimeters. So they are very well measurable. So here you see the typical profile of, in fact, the two mesons which are in the forward region. On the other end, what is really interesting in LHCb at the energy of 8 TeV with 100 GeV, that of course when you produce BB meson from gluon splitting, of course this BB meson, of course what you observe at the final state are hadrons, okay, with the normal way of fragmenting from partons through the hadronization to get hadrons in the final state. What's important, of course, any kind, all the type of hadron can be produced. So you have, of course, all the B sub U, B sub D, strange B sub S, B sub C, and also all kind of baryon are produced, and at the end you have two hadron in the final state. So, what is the characteristics of LHCb? Is that the BB production cross-section is huge. Of course, you have a lot of inelastic procession, and of course, at the end, the detector is like resembling a sort of fixed target experiment, even if you are not in a fixed target experiment, because in fact you have, for instance, if you have, for instance, the two collisions, you have events which goes like that. While I show you later that in Atlas MS the collision are more on IPT. So if the direction of the beam is like that, in LHCb the particle fly like that, while in Atlas and CMS they are at large PT, and this due to the different physics. So this is the LHCb detector, where you see, in fact, you have a PP collision here. So and there are several detectors which helps in reconstructing particles. So you start from vertex reconstruction at very close to interaction point, because here you want to measure very precisely the decay of the B mesons. As I said, few centimeters, but you want to have a very precise information about that, also to measure lifetimes and different characteristic, oscillation, and so on. So you have a precise detector, which I show few transparency, the silicon detector. And then, of course, you have two Cherenkov detector. Cherenkov detector are for separating pion, kaon, and proton. So you do particle identification. Then you have a tracking system here, which I indicated here. So the magnet, get information about the curvature and so the momentum of the particle. Once that momentum and the particle pass reach, you get the velocity, and so you get information about the particle. And so, as usual, in the last part of the detector, in the farther part of the detector with respect to interaction point, you have electromagnetic calorimeter, hadronic calorimeter, and the muon channel. Here is the muon system. So it's a quite a typical high energy detector in colliders with this particular structure, which all the physics is almost in a forward region. So instead of being, as we will see for Atlas and CMS, just around the beam to collect the particle like that, is just to collect the particle in the forward region. So now, just two words about the vertex detector, maybe also to compare with the others, which I will not tell again in the rest. So you see all these experiments, Atlas, CMS, and LHCb, and then here I compare with the future linear collider characteristics. They have a vertex detector because it's very important to tracking, to make a precise tracking of the particle, and of course when you track the particle as close as you are at the interaction point, and what really counts is the first point near to interaction point and the last point far from that, because you need to be precise here to have a large lever arm in order to do a very precise trajectory. So you see that the characteristics normally of this detector are area, channeling, and so on. So this I probably come back. So this you see that in case of Atlas and CMS, you have in one case large area or large number of channels. But what is very important here that I want to underline for LHCb is, of course, you don't need large area, but you use the detector for triggering. Then it's very precise. It's very important because you want really not only make a tracking, but you want really to have precise vertex reconstruction. And since it's close to this, you have you have a very precision. Of course, you have an important, so you put it very, very close to interaction point. You see how closer it is with respect to Atlas and CMS, really to have a very precise vertex reconstruction. Finally, for this reason, so this is quite quite important characteristic. So then eventually you can compare with what you construct in future. So this detector is located very close to the interaction point, so giving a very, and is a very precise, and so these characteristics together allows to do almost what? Almost, for instance, so here is a picture, almost to be able to reconstruct lifetimes with just a fantastic precision. Almost, I would say, these measurements are not just a single measurement, where are almost used to be sure that your detector is correctly aligned, and so it's done with really, you see, I mean, 36 inverse picoseconds. So because the rest is completely dominated by systematic. So here really is a sort of cross-check that your detector during the running is always well aligned. So it's a sort of you measure lifetime almost on real time, and you can align your detector on real time. So this is rather impressive if you think that this measurement has been done during, I don't know, 20 years, and here you do similar precise measurement using just data which today we collect 36 inverse picosecond in one film, just in few, yeah. So this is a rather impressive. So and here you see the detector. So and then also this detector, maybe then if you have more technical question, also Sergei is there to answer, but you can move out of the beam and in on the beam when you do the fill of the beam, in order not to that. This is a quite impressive technological achievement, that since this is very sensitive to radiation, and you have to be precise, it's continuously move out of the beam and in the beam, because when you ramp and you fill, there is a lot of noise, and this detector would be damaged, and so you pull a bit out of the beam and then into the beam, and by always, so you move all the time, and even by that is always so perfectly aligned that you can do this measurement. So is really a jewel, this detector. Okay, here you see that from time to time, even if in LHCb you try to reduce the number of interaction per event, because this you will see in LHC, in CMS and Atlas, you can have more than 20, 30 interaction per crossing. Here you try to reduce it maximum. This is the reason because you know it go down. But you see that you can even distinguish a few vertices in the same crossing. Okay, and this is a similar way. So then the particle, the reach, you have reach 1 and reach 2, and then you have a very good kaon, for instance, efficiency with an excellent kaon pion separation. And what is very nice to notice is that by using these two, the Cherenkov at a different medium and so on, so you can really make an excellent kaon pion separation running from 2 GeV up to 100 GeV. So I mean you have a large range of separation with a rather good separation between the kaon and pion. And again, here you show that in fact Cherenkov detector is you reconstruct rings, and then for instance this is belonging to the kaon hypothesis. You see how well you manage to distinguish kaon hypothesis. All the dots really belong to the ring, which is related to in fact the aperture of one of the beta phenomenon of the Cherenkov emission, I mean the velocity which is given by this. So you see how precise you are, and this is a bit like a sort of advertisement plot, but it is rather, I think, impressive. For instance, if you want to look at phi to k plus k minus, where you have to reconstruct two kaons, you see that without using any PID from Greek, you don't see anything. When you apply that, with a rather good efficiency, you can reconstruct very precisely. In fact, you see the phi peak coming out. So you see with a very small background. Of course, here the cuts are quite severe, so you reduce quite a lot of also the signal, but by the way, you are able to reconstruct very precisely the phi to kk. So I think here there are really the two detectors which quite key detectors, I mean precise tracking and vertex reconstruction and precise particle identification. So of course then you have to go further, because you don't need only to identify kaon, proton and pion, but also photon, electrons and hadrons, and this is done with the calorimeter, so you see a nice phi0 peak, and also muon detector. I will show results in BSAS and mu, where the in fact muon detector is very important. Now, few words on CKM. So what we are doing, which is so I terminated on detectors. Now I move to the goal of the physics goal of LHCb. Which are the physics goal of LHCb is to continue the program which has been initiated since many years, but in the last years where the leaders were Babar and Bell at the B factory, is to continue this work and push at the extreme precision, at unprecedented precision, the measurement of what? If you want to test very precisely what is the fermion sector of the standard model, so which is related to, for instance, the fact that, for instance, for charge current is coded in the CKM matrix. So if you want is to test further the CKM mechanism, and of course the fact that you know that in the standard model there is a single parameter, a single complex parameter which governs all the CP phenomena which can be observed. But of course you want to push that further in order eventually to look for new physics or new CP phenomena which are not explained in the standard model. So this is often a practical way of showing, of putting all the measurement in a single plot is done by a unitarity triangle, where you exploit the unitarity of the CKM matrix, and what you do, you reconstruct a triangle in a complex plane, where in fact the apex of this triangle is given by the coordinate rho and eta, so it means that when surface is not zero, if eta is different from zero. And then, okay, I cannot go into detail, but the measurement of the size of this triangle are related to, for instance, these two semi-electronic decay, this size is related to the oscillations, and the angle are related to the measurement of a CP violation in, for instance, in B physics. So many of these measurements, semi-electronic decay, oscillation, measurement of CP violation, concern B meson. So B physics is playing a crucial role in trying to determine precisely this parameter. Of course, the game is not only to measure precisely those parameters, somehow is interesting per se, since they are free parameters of the standard model, but is even more important because you try to look for discrepancy. So you want really to measure, to over-constrain this triangle, to measure, to do many measurements, and then to try to compare these different measurements, and hopefully to find the new physics, because these constraints, they do not match one to the other. So one example is that just LHCb has to start to a situation which is already quite precise. So this is the situation, the state of the art, that we probably have already seen a few times, when you put all the measurement worldwide in a rho eta plane. So you see that we got already a very good precision, in the sense that you put, okay, what are these color plots? These color plots are the single constraint. For instance, here you and you color the probability. So you say that the constraint of UB tells you that rho and eta should stay inside this circle. The measurement of beta says that rho and eta should be inside this green part. The measurement of other quantity says that, and then when you put everything together, you can fit, and finally you have two information out of this plot. One information is that rho and eta are very well precisely known, but what is really impressive today is that after all the effort we have done, that eta is known already at 4%. So you will see that, it's very far from zero. So CP violation is being firmly established, 4%. But then the duty of LHCb is to do even better than that. Why better than that? Because if you want, this plot is a sort of a triumph, but is a sort of enormous deception, because you don't see any discrepancy. You see that this plot is showing you that the constraint coming from semi-electronic decay, from B oscillation, from CP violation, from many stuff, are all compatible one to the other, telling you that the CKM matrix is really the dominant source of a flavor mix in a CP violation. So somehow this is a plot which we can spend much more time, which is showing you explicitly the triumph of the standard model in the fermion sectors. After the triumph of the gauge sector by precise measurement of radius correction, here you see that somehow everything is compatible. So the duty of LHCb is quite tough, in the sense that you have to improve this situation, because you want to further test this paradigm of a standard model that, come on, we don't want to die all with the standard model still alive. So we have to work to kill the standard model, because this is our job. We are a serial killer of the standard model before standard model kill us, because is a terrible fight so far, because it's very resistant. So it's a sort of mutanism. Okay, but so the job of LHCb is very tough, and today I have not much time to show you all the beautiness of the results of LHCb. I will show 2 or 3 of them, because Alexander told me that I have more or less 4 hours for a seminar. It's true, no? No, less than that? Bit less than that, no, 2 or no, 1 hour. So I show you that, for instance, LHCb can measure this angle, gamma, with a very high precision, and then I show you also some rare decay that can measure with very high precision. Okay? So this is a bit complicated issue. Maybe is from some flavor physicists in the room, which I think are there. But I want just to tell you that there is a without going in explanation, because otherwise it takes probably too much time, but that in fact this angle gamma can be obtained by study this final state, which is d0 k. Okay, this is rather simple to understand that this is related to direct CP violation, because you see, this is just, okay, probably very simple what I'm saying now, but CP violation occurs when you have two different paths to reach the same final state. Because when you have two different paths to reach the same final state, there are two amplitudes. Amplitudes are complex number, so you have to square A1 plus A2 squared, so you have interference. If you have just one path to go to the final state, everything is real, there is no interference, okay? So you have always to find two ways to go to the same final state. When you have two ways to go to the final state, you have CP violation. So what has been found by those gentlemen, which are here, Gronau, London, and so on and so forth, is that this is very interesting channel. So because you see that you have two paths to reach the same final state. But in fact, there is a little trick there. But in fact, you see that in one case you have D0, in the other case you have D0 bar. So in the case of D0 bar, in fact, you have to, and this is the existence of all these methods, you have to find final state. So you need the D0 and D0 bar going to the same final state, that at the end the final state is really the same final state. So, and there are several ways of doing that, so there are three methods, okay? So one, for instance, was also introduced by Yuval Grossman, which will come to Kharkiv to teach this summer, in fact, in the summer school, okay? So, so here you see, so this is a rather tricky method, but by studying that you can make a study of gamma, because in fact you can realize after some calculation the interference of these two diagrams is of course related to the strong phase shift between these two diagrams, but the weak phase shift is exactly the angle gamma we want to measure. So at the end you do some measurements, so you see there are very rare decay, but so far LHCb may start to measure this decay, okay? So can measure this decay, and finally today is able to start to measure the gamma angle. So what I wanted to show you is that today LHCb alone is already able to measure gamma. This is gamma with a strange character, but it's supposed to be gamma in Dell. Before being converted to Macintosh, is gamma. And this is you see that it's able to measure this angle gamma. Maybe for not expert is not telling much, but this precision is the equivalent of the precision we have more or less so far by putting together all the experiments in the past. Okay? So LHCb alone is really starting to be the real player of measuring of gamma with a limited statistic, and so means that soon this constraint, so you see that this constraint is the angle gamma, so in violet, so this constraint will really shrink by the measurement of LHCb. So this is something, one of the strong motivation of LHCb experiment. Now I want to spend maybe the rest, still 5-10 minutes on LHCb before going to CMS and Atlas. There are very interesting transitions. We have experts here, which are this best transition, and I want to show two examples. So, okay, then I realized that I put maybe too much formats, but maybe it's useful for people working that. But in general, these transitions are very interesting. Those decays are rather rare. Okay, the point is the following. Often, what we want, when you want to go to look for new physics, what you do, you try to go to decay which are very rare in the standard model, because in this way, in principle, a new physics, Lagrangian, could eventually not share the suppression you have in standard model. So So which is one of the main suppression in standard model in the flavor physics? Is the flavor change in neutral current. So you know very well that a B quark cannot go directly to S quark through emission of Z0 because this is forbidden by standard model. Z0 is diagonal. So to do flavor change in neutral current, you need to pass from a box diagram. So you need to pass from a double emission of W. So flavor change in neutral current. So the current cannot a B, which is minus 1/3, cannot become S minus 1/3 by neutral current at the first order, has to pass to a second order by double emission of W. So this is somehow a rare decay in the standard model, but eventually a new physics structure eventually do not share that. So flavor change in neutral current, so B sub S transition, B to S transition are rather interesting. So one of the main, okay, this is showing that we are serious people, theorists are serious people. And so one of the growl of LHCb was to study this B sub S to mu plus mu minus. So this is an extremely rare decay. You see that the standard model, due to the fact that I said you have to emit somehow a W before coupling, because B sub S cannot just go to this vertex and emit as a Z0, but B sub S has first to be transformed in C quark, S in another C quark in order to be diagonal, and then here you are diagonal, you can emit as a Z0. So you see that this decay is extremely rare, and the standard model predicts to be of order 10 to the minus 9. Of course, this could be enhanced a lot by new physics for the reason I said, that eventually, I mean, new physics do not share all this suppression, because this suppression is double. There is also G mechanism in that. But okay, so this was intensively studied, and so you see that is, I think, is a very nice plot when you see mu plus mu minus, mass of mu plus mu minus in terms of candidate. You see that you have several resonance you know very well, and so here you want to look at the peak. Somehow you want to see, you see a small peak in B sub S going to mu plus mu minus. So now the result is that LHCb this summer was was in Japan in October, I think, announced in fact the fact that there was a first hint of you see that there is not yet an evidence, there is not yet an observation, because I mean can be also still a fluctuation, but you start to see a signal here located at the B sub S mass with a 3.2 10 to the minus 9. Okay, if this is confirmed, okay, is a fantastic success again of standard model, but again a dramatic deception, because again we go look in branching fraction of order, the standard model says should be 3 10 to the minus 9, and we find a 3 4 10 to the minus 9. So so it starts to be really again another prediction on the standard model, which seems to be okay. Now we are at the level of 2.5 sigma, 2.7 sigma, but I mean still I mean very compatible with the standard model. So here you see a nice picture out of many tracks. You see in fact mu plus mu minus in that. So I want just to spend again 2-3 minutes in saying that there are very complicated analyses, and this is something that renders also our job of experimentalist, I'm an experimentalist, very interesting. That data analysis is really a nice job, in the sense that you have to find so at the end again you have to extract the signal and fight against backgrounds. You have to find intelligent variable to separate the signal and backgrounds. You have to understand from theory up to the extraction of the signal. And this is for instance, to do this analysis B K star mu mu, which is very interesting for new physics, is extremely difficult analysis, because you can say that this is a vector. So when you have a vector in the final state, you know that you cannot just terms of, it's not like a scala where you have just one observable, but here you have three angles, and so you have to parameterize your decay width in terms of your differential width depends on not only on Q square but also on these three angles, because there is a presence of vector in the final state. So it's a very complicated analysis because you have to measure not only the events, but you have to measure events in bin of all these different variables. So you have 4 parameters which depend on Q square. So so it's a very, very complicated analysis which is today's master. So I think it's a lot of satisfaction to be able to master this kind of analysis. So what I want to show you that often from this analysis we try to extract some simple variable to plot, and this variable is, for instance, the forward-backward asymmetry. So in the sense that eventually leptons, I mean, there is in fact the symmetry between the particle, for instance, lepton or K star, emitted in the forward or in the backward direction. What is very interesting in this analysis, which I'm running a bit, is that in fact we start in LHCb to measure this. This is a forward-backward asymmetry as a function of the Q square. And here again, what is rather interesting is that the standard model predict the shape of that and predict also the position where this forward-backward asymmetry cross 0. So, and in fact, in the previous plot, but which I escaped a bit rapidly, you see that standard model is like that, but extension of the standard model like supersymmetry predict a completely different shape of this variable. Again, after this very complicated analysis, LHCb is really finding something, or you can see it in this way or in this way, you can find, he finds something which is rather compatible with the standard model prediction, you see, and even the crossing is rather compatible with the prediction of the standard model. So you see that even in so this is what I think is very interesting in this experiment, that we managed to do a quite complicated analysis, and sometimes theorists propose very interesting ideas. Those implementation is difficult from experimental point of view, but quite rapidly and ingeniously the experimentalists managed to do these measurements, and eventually once again to confirm that still the standard model is the good model, is the good theory to predict both the shape and where this asymmetry touch to 0. So just to show you that I forgot something in LHCb, is to show the snapshot of LHCb results. So there are many of them. For instance, I show you that, and I show you, I don't know where it is, BS in new, few of them, but there are a lot of results on LHCb, plenty of different decays, and all that contributing in trying to get an information on, I show you that, for instance, that and another one. So contributing in getting information about flavor physics and fermion sector of the standard model. And so far, the point is that, as we summarize here, flavor physics is an excellent place to hunt for physics beyond the standard model. We have in LHCb excellent detector, good quality of data, theorist and theory which is available, and behind it. At the end, I would say that there are future directions. We have to improve many of the measurements we are doing today, and I would say that the first message I want to give you is that so far no effect from beyond the standard model has been observed after, I would say, these first 2 years of data taking, but more has to come. As I said, confirming BS in mu and doing other measurements like, for instance, increasing gamma precision. And then another point which I didn't stress much, but again, LHCb is produce a lot of B mesons, but it's also producing a lot of charm mesons. And of course, charm physics is extremely interesting because maybe the next frontiers of precision is trying to get as precise as possible CP violation in charm system and precise CP violation in charm system, eventually flavor changing neutral current in charm system, and LHCb is well situated to do all this kind of measurement. Okay, so this was a summary of LHCb. Now I move to Atlas and CMS detector and results. Since I discussed quite a lot already the detectors, I will be brief on detectors here, and then I will concentrate more on Higgs result. So again, okay, here is just to show you that detectors in real view are impressive objects, which this is really the most complex object detector which has been never constructed, and you can see that it's really this shape of being barrel. I mean, you have a barrel, and then at the end you have a forward region. So the detector, just to give you an idea, have something like 140 million data channels, okay, and these are observed, I don't know, something like 40 million times a second. So it's something which, of course, give you the complexity of this object. So here I show you an example of a CMS, also because Maxime is working on CMS and prefer to show CMS than Atlas. And so here again is showing again the complexity of this detector, and instead of showing in case of LHCb I show more performance. Here I show real object. So again we have a silicon tractor we have discussed before. We have scintillating crystals, the chamber to do tracking, and also the plastic scintillator. So you see, I mean, again, this detector is always done like this, with a central region where you have a precise silicon detector, then you move forward and forward, and when you go up to here, you have a electromagnetic calorimeter up to muon chamber. Again, this is a silicon detector. Just I show you silicon detector. This is again CMS silicon detectors, and here what we want to show you that in case of this large experiment, was not the case of LHCb, where the idea was to put it as close as possible interaction point, was a small detector. Here you see that in terms of number of electronic channel or surface, you see that CMS and Atlas, they can stand really in front of all the previous detector, both in terms of electronic channel and the silicon area. So now we are in this business also experiment like gamma detecting experiment like blast Fermi are reaching similar surface in terms of area. Okay, and this is the electromagnetic calorimeter. So maybe one point which I did not discuss for LHCb but is valid every time is that everything starts from a really detailed work on detector simulation, which means really detector simulation up to a really tiny effect. For instance, just to tell you that I don't know, you have to simulate both. I mean, the detector response at the level of real pulse shape, up to also being able to detail the beam branch tractor for the pile-up simulation. So really, of course, you rely a lot on simulation. You have to work a lot on detector simulation, and once you have tuned up, you try always to rely on data-driven method. But this I wanted to show because all the results are due to the fact that not only you have a very nice detector to detect, but a lot of work in order to make this detector performing at a nominal performances. Now, here we start with the X mass. So here there was a little animation that you probably, I go to the end of the animation. Okay, was like that. So, which shows the following, that you know that from precise measurement you have a sort of indirect search of Higgs, in a sense that by doing a precise measurement related to the gauge observable, you can, this was a big success when Lab was able to predict the mass of the top before the top being discovered. So this was an example, and this was particularly successful because this relative correction goes like mass to the top square, so the top indirect prediction was very precise, and then the mass was measured by Tevatron. In case of Higgs, the situation is slightly less precise because this was like a logarithm of the mass of the Higgs, but by the way, you see that Higgs masses before the results I show you was predicted to be in the range of not greater than 100, should be limited at 160 GeV, and even with a minimum below 100 GeV. On the other hand, also this plot shown that two of the most sensitive variables to give information of the mass of the Higgs was the mass of the W and the mass of the top, which in fact select more here light X, okay, with light X, which you see here. Okay, this plot tells us much more, but maybe if you have questions we can comment. But so when LHC start, a lot of measurement has been done, and I like to show this plot because it's a very nice understanding of the standard model at 7 ATV. So you see that you measure the W, Z decay, here you measure W gamma, Z gamma, WW, WZ, ZZ. I mean, all this was measured, and all this channel contain, for instance, W cross-section with more than 1 jet, more than 2, more than 3, and everything was and is, you see, very, because these are prediction, okay, prediction at 70V in blue and 80V in green, and the point are measurement done. So you see the fantastic precision of all the agreement between prediction and theory, both done in Atlas and in CNRS. So somehow we can say that all these were tested. As I said, you put one W, one Z, then you start W with gamma, Z with gamma, then 2W, 2Z, and so on. So, and then of course you go down in cross-section. And of course this shown that we were completely ready to go onto the X, where the cross-section of course is slightly lower. Okay? Because you can see somehow is a test of the standard model, but you can say that the standard model are sort of a background processes for searching for X. So you need to master that before going to the X. So now this is, you know very well, that the historical 4th of July, where in fact the collaboration presented the discovery of a Higgs boson, and after that I think this was really the historical date, and then I'll try to say a few words on how this discovery was possible. So first of all, just few words. The standard mode X is produced in LHC by several mechanisms, which can be gluon-gluon fusion or TT fusion going to X, eventually Brent-Strahlung, which was similar production at Lab, at the plasma machine, or this other production, which is how it's called WW or ZZ fusion. Okay, so and each of them has a different dependence, cross-section versus the mass of the X. All those contribute to a final cross-section, which is given here with all the calculation at the next to in order, plus also, I mean, they are calculated at a great precision. Okay, so good. Now, just to give you an idea that so let's say you can produce a lot of Higgs boson with a given luminosity at 125. Now, for what concerns the decay width, so
is the branching fraction, also with uncertainty, as a function of the mass of the Higgs. So the natural width of the Higgs boson, okay, now of course the natural width of the Higgs boson depends on the mass, it's clear, but when you stay at this mass, around 120, 125 GeV, the natural width of the Higgs boson should be 2 or 3 MeV. Of course, this natural width increase when the mass is increasing. Somehow is one of also the characteristics of the Higgs, that if you go too far in mass, if you go above 1 TeV, the mass of the Higgs is so large that it's even difficult to consider Higgs as a particle. Okay, so one of the problems of the Higgs, if you don't find a below mass, means that it's not anymore a particle. So, but at that mass, the Higgs width is few MeV. So means that in general you are not able at LHC not really to reconstruct the natural mass, because you rather see the detector, the resolution mass, not that. You have only 2 channels where you can maybe have such a resolution, even if it's rather weak. But okay. So what is interesting that if you are at 125 GeV, this is really a mass which, if we had the choice, we would have chosen that mass, because you see that if you are too low, it's a bit boring, because practically the bar is dominating. If you are too high, it's rather boring, because almost bosons dominate, Z and W. While this mass is really a good one, because you can produce, you can have a BB bar, WW, ZZ, and I will show you that is quite surprising, but also gamma gamma, which is only 10 to the minus 4, but you will see that is the channel which contribute more to the Higgs discovery due to the cleanness of the experimental observation, just 2 gamma back to back. If you have very well understanding of your detector and very good detector, you can do it. So somehow, why I'm saying that? Because of course now when you okay, I gave as we have observed the Higgs as I showed you, but eventually when you observe Higgs, you can observe Higgs in many different decay modes, and so you can establish if the Higgs is a standard model one, because okay, you know that this coupling here are given by the fact that the standard model Higgs is coupling depending on the mass of the particle, since it's the particle which is responsible of giving mass to the fermions and to the bosons. Okay, so now this is the first. So I move to gamma gamma. So gamma gamma is the signal is coming from this kind of diagram. So of course gamma gamma to produce Higgs to produce a gamma gamma has to pass through a triangular diagram like that. So is a suppressed decay, and of course you have a lot of background, which is normally, I mean, to find the 2 gamma in the final state is rather simple, in the sense that you have QCD processes, or Compton, like one gamma here and 1 gamma radiating 1 length of Q over quark and so on. So there is a lot of background, and on top of this background you have to find the signal. So I have no time to describe the analysis, but you see that even if the background was quite severe, finally people, experimentalists, managed to find a good variable and the detector working so well that you can see that you see the peak here over the background. When you subtract the background, you see a clear peak, okay? And in this case, again, for CMS. So the fact of weighted and unweighted is just a technical, because here is not a physical plot, because you make enter each of these entrances weighted by S over B, which is really what the likelihood effectively see. So when it's analyzing your plot, because in fact this is more complicated than that. There are a lot of the sample divided in several beams and so on. But but the final results you see even by eyes, you see clearly this peak, peaking at 125, and of course also here key issue is the energy reconstruction of the two photons and the angular resolution of the two photons. So you have two photons, you need to know very well the energy of the two, and also have a precision on the relative angle between the two photons. So this I think would stay for years, centuries, like sort of a textbook plot where you see X going to gamma gamma. Okay, now, okay, this is supposed to be an animation, but I know doesn't work. Okay, not very important. So no X here. Okay. Why you have another golden mode. Why is a golden mode? Because in principle you have X going to ZZ, and if you Z, each of these Z goes to 2 leptons, you have 4 leptons in the final states, and each of the 2 leptons, if you pair well, peaks at the Z0 mass. So you see that also here, you see that with the X signal at 126, you expect you expect this signal, and you see that there are some accumulation of events here, so that you have a peak which significantly peaks around 126, and all the rest of the background, which is ZZ or Z gamma, have a different shape, and so this is a clear signal above the background, and here you can see the collection of this signal on this plot on the mass of the first and the second Z. So of course you have to think that you go to ZZ, but since the mass is 125, is a ZZ star, so one Z is heavily virtual, is the reason because the cross-section is not still very high. So the fact that the cross-section of ZZ is still ramping up is because one Z is heavily virtual, okay? Then okay, this thing is due to the fact that WW reached the non-virtuality before, because the mass of the W is empty, so at 160 both W are real, so you have and then when the ZZ goes up is when you reach the 2Z real, okay? So the fact that there is a ratio 2 between WW and ZZ is due to the Pauli principle, because Z are identical particles, while these are plus and minus, okay? This is the reason. But by the way, you are here, so the Z, one of the Z is heavily virtual, okay? So, and then is the reason because when you plot that, you see one Z is real, what you say, on shell, sorry, and the other Z is off shell. You say how heavy is off shell, is a Z at 25 GeV, so this is quite, so you see there is this combination, and you have events that can be 4 electron, 4 muons, or 2 electron and 2 muons, okay? So this is quite significant. Now, this shows the same in Atlas. This has been published, where you have gamma gamma, as I showed before, 4 leptons, but then there is also another channel which contributes to the discovery, which is WW star. Okay, this is a bit more difficult channel because you have WW, and then you look at W going to lepton neutrino, and the other W going to lepton neutrino. So you have 2 leptons of different sign, but you have 2 neutrinos. So of course you cannot reconstruct precisely the mass because you have 2 missing neutrinos. And of course the background is more important because all missing particle cracking the detectors contribute to your background. And but finally, you see you don't see peak like in here or here, but the peak is much broader, but you see that the data would not fit with simple background, while you need in fact signal to explain this extra bump, these extra events on top of the background. And this is X going to W star. Okay? So now, okay, this is the update. We have X gamma gamma, X WW, X ZZ, but not only. Of course, we want to study also X to tau tau and X to BB bar. Okay, if we go back to to the previous plot, okay, you see that so far we have studied WW, ZZ, and gamma gamma. Okay, there are reasons for that. This is very copious, but you have missing neutrino. This is very simple because you have 4 lectons in a final state, but the cross section is low. And gamma, also experimental, you can see with the cross section, with the branching ratio very small. But what about BB bar, which is rather large? Okay, okay. There the problem is that the BB bar are quarks, and now it's very difficult in the experimental environment of Atlas and CNRS to be able to distinguish Higgs going to BB bar and then hadronizing, and then in all this, let's say, forgive me for that, in the mess of that, it's very difficult to recognize these 2 jets and to reconstruct the 2 jet mass and to go back to the Higgs mass. So even that, which in principle should be the most copiously produced, still we do not really observe Higgs in BB bar significantly. Then there is tau tau. Also tau, you see that is larger, but why tau is difficult is the same reason, because tau is even more difficult than WW. Why? Because you have X going to tau tau, but suppose that you want to do tau in tau, you have to go, for instance, you want to go to leptons, so tau go to what? To lepton and 2 neutrinos, okay? And the same for the other tau. So you have 2 leptons but 4 neutrinos, so you lose a lot of energy, you have a lot of energy missing, so it's even more difficult from experimental point of view. So tau tau and BB bar are the next branching ratio we would really want to measure at 5 sigma, but they are experimentally rather difficult, okay? But there is work on that, and I show you that we start to measure. At that point, there were the new frontier. When we stop here, there were the new frontier. Now you see that, okay, so here, you see in fact that you measure, you start now, okay, this is precise, then you see that after all this, even these 2 channels, which were foreseen to be very difficult, now have been measured by both CNRS and Atlas, mostly by CNRS. So what this plot is telling us a very important thing, that in principle we find many decays of X, and all this seems to be in agreement with the prediction of this particle being the X of the standard model. Okay? Now often you see this plot, okay, this plot in spite of having all the different channels in, you have what is called the local p-value. Okay, is a concept. Yes, I mean this is telling you which is the probability that the signal, the excess that you have seen, is just to be attributed to a statistical fluctuation. So this is the translation in words of this statistical concept. And you see that now we got an impressive significance, because we say that the probability that what we have observed is a statistical fluctuation is at the order of 10 to the minus 11, which corresponds, if you translate this in terms of Gaussian distribution, to a 7 sigma significance. Okay? So this is the way you have to read this plot. So we make very sophisticated for at the end a simple message, but it should be very sophisticated, because I mean, when you are at 7 sigma, you don't care. But when you start to have 1 sigma, 2 sigma, 3 sigma, of course, and when you have to cross 3 sigma to be able to say is an evidence, and you have to cross 5 to say is an observation, I mean, then statistician, I mean, they have to do, we have to do all this work in order to be sure. Okay, one plot similar that I want to show in Atlas I want to show you because it's giving more or less the same information, but it is not now split in different channels here, because it's here, but in time. And I like very much this plot because it's showing you that in fact the construction of this observation was, as you know, a bit stressing because we start from July 11, where the evidence was at 2 sigma. Then it went a bit better. Then we go very far, so we were almost sure we got it, but then we come back. So we say, maybe this was a statistical fluctuation, but then finally we go down, and then we go up to 10 to the minus 9. So you see that in 2 years, we start from the first evidence, a bit of oscillation around evidence or not, down to, in fact, the fact that it was filming a Higgs boson. So now, if you look in terms of a channel, you see that most of the contribution is given by gamma gamma, which is an information to. Okay, now what you measure, important, you say seems to be a X, and seems to be the X of the standard model. Okay, so now which is the mass? Okay, the mass is started to be measured using the two most clean channels, gamma gamma and ZZ. And you see gamma gamma in green, ZZ in red, or if you want in light in here, or here if this one is a standard model, okay, and in terms of mass, you see that you have a slight excess. I mean, gamma gamma is a bit too high, while Z0 is perfectly, ZZ is perfectly standard model light. When you put the two together, you get here a mass which is 125.8 plus or minus 0.4 plus or minus 0.4. So the mass of the X is rather precise in CNRS and is also rather precise and compatible in Atlas, but with a slightly high systematics because Atlas has a slight tension between the measurement of the mass. In fact, the mass selected by the channel ZZ is slightly different than the mass selected by gamma gamma, but the tension is at the level of 2 sigma, so probably nothing, unfortunately, because we always would like to have something new and not expected, but it seems to be a statistical fluctuation. So here again, the message is to tell you that the mass of the X is now quite precisely measured, again with an error which is around 0. If you combine the two, probably you can stay around 0.3, 0.4 G. What next? Next, we want to know if the Higgs boson is a scalar or something else, because the standard model predicts that the boson, Higgs boson, is a 0 plus. Okay, is a scalar. Okay, by the way, would be the first fundamental particle, scalar particle. So, of course, since it decays in gamma gamma, it cannot be a vector. X to gamma gamma means that or is a scalar or is a tensor, okay, because it goes to gamma gamma. Now, okay, which means tensor would be just a fantastic stuff, but unfortunately, what we are observing, then can be 0 plus or 0 minus. So what we do that we try to do angular analysis, as usual, when we have to get both the spin and the parity of the particle, we try to separate. So it seems that is much more probable that is a 0 particle and not 2 particle, and this separation is at the level of 2 sigma. Now in this plot probably was only out 1 sigma, but also Atlas has measurement, and I can tell you by some insight that in Morion it would be much more than that. So I think in Morion next weeks the spin of the X will be firmly confirmed. So it seems to be 0, and then between 0 plus it seems to be 0 plus. Okay, so this is. So maybe before concluding, we can say, and what about new physics? Because okay, standard model, the Higgs discovery is just a triumph, it's clear. And the confirmation that this Higgs is probably, now we are almost sure, that seems to be very, very standard model-like. Because the branching fraction seems to be at 10%, 15% precision, those predicted by the standard model. It's practically confirmed that is a zero plus particle, so it's a scalar needed in the standard model Lagrange in order to give a mass to the particle. So, is there an hint of new physics? So I show you just one plot, which is impressive plot, where you see that physicists in Atlas or CMS, they are desperately looking for new physics in many, many, many different channels. And you see that on supersymmetry, but even, okay, here is just a plot of supersymmetry, but I would have 2 or 3 other plots when you look for Z prime, for Technicolor, and so on. So far, all the indication is these are limits, okay, with some hypotheses, but in general, all the indication are that there is no new physics, there is no new physics up to the TD level. So there is a strong message out of that. The strong message is that we have discovered the Higgs, we have intensively looked for new physics. For the moment, the Higgs is there, but there is no new particle from the electroweak scale up to the TD scale. So you know well that one of the motivation of LHC was a sort of idea that we should have found new particle at the TD scale. So we are almost there. Okay, for certain model we are already at 10 TeV. I mean, for Z prime, I think we are at 2.5 TeV or even more. So for a moment, the new particles are not there. I mean, so we are walking a bit in a desert. I mean, the desert is not like yet a Sahara desert because it's just from electroweak to the TeV scale, but so far there are no new particles appearing, which make the run at 14 TeV particularly interesting because we can explore a new frontier. So this is what I would end up my seminar by saying that of course there was a fantastic triumph, but I would say also terrible deception so far, because Higgs is discovered, so people would say, okay, come on, people, Higgs is discovered and you dare to say that you are a big deception. Of course, Higgs discovered a standard model, but there is no evidence of new physics, and my message today is that neither in precise flavour measurement, despite of very nice work done by LHCb, neither in direct search with the work done by Atlas and CNRS. So of course, we have to go on in exploring that. And this I show for Atlas. Here we are just here. Now we have a shutdown, but then in end 2014 we go back to 14 TeV. And I like very much to call it phase 0. It's nice to call it phase 0. It's ambitious because since we did not do anything, so we start from phase 0, while in fact the phase 0 was up here. But this we call it phase 0, which is a bit funny. But okay, we start at 13, 14 TeV, and then hopefully after a few phases, we try also to increase dramatically. This is in French, sorry. Going dramatically up in luminosity in order to have 3,000 inverse femtobarn at 14 TeV. Now we have just collected 20 inverse femtobarn, so 20, so 100 times less at 8 TeV. So I think there is hope that also new physics will appear and the deception disappear. Okay. Thank you very much.
Thank you very much. Okay, now question. You agree that new physics absent in this region?
So invite also Maxime and Sergei for a question to participate for topics they are expert in. Yeah.
Павел Владимирович.
First, I'd like to thank you very much for the excellent talk. So no evidence for new things, but how about indication? You didn't mention an exciting result that was reported by LHCb last fall on visceral D decays to muon pairs. And this, if it's true, I mean,
Which
almost 4 sigma excess over the standard model background. You know that B0D decays to muon pairs suppressed by almost order of magnitude here compared to
Yes.
B0 is S.
But there is no 4 sigma evidence in mu plus mu minus.
But LHCb reported on considerable excess over the standard model.
No, not on BD. Excess was, no. B0D mu plus mu minus, so far in LHCb there is no evidence of sigma.
Really?
Yeah. I would be happy to, but no. I can ask Sergei.
No, I'm not aware of
Yeah,
that.
no.
Submit to review because to what I know, it's perfectly consistent now with
No observation.
With no observation.
Really?
But on
Yeah.
the other hand,
But that was taken up to
I think it's K5 or some. There was some
yeah, I mean,
yeah.
there are many interesting things. But maybe what is relevant is that the significance of this best in BD, I think, which was completed at the end of the year, was essentially 3 sigma, despite the error, but when looking to significance.
Yeah.
So and this starts to be significantly different from 0.
Okay. Thank you.
No, I think it's B sub S.
No, this was published in an application.
No, I think it's that. I mean, it's B sub S. B sub S is no sir, but B sub D. You're right. I mean, it would be a clear signal and is probably the next frontier in this mu plus mu minus decay, but it's a bit far because it goes like VTD divided by VTS square. So VTD VTS is a factor 20 even because 0.04. But then there is correction, so it's a factor 10. So we expect B sub D with all correction being of order 1 or 2 10 to the minus 10. So to address 10 to the minus 10, you see that you need, if you are not clever enough, 100 times the statistic to go there. So it seems to be out of the reach of the LHCb phase now. Maybe upgrade is possible. Eventually, is a channel that if CNS and Atlas they have a trigger to trigger on muons, since the luminosity is very high, eventually they can be seen by Atlas and CNS.
Yes, I know this, but LHCb reported that they allegedly saw the events.
Okay, another question. Alexander.
We showed results for studying also the nature of the Higgs, whether it is a scalar or pseudoscalar. So how solid is the conclusion that Higgs boson is a scalar?
No, not yet. Not yet. No, not yet. The analysis is very complicated, and they are pushing a lot, both collaboration, because I mean the point is that now all the data which has been registered are available, and then there is a conference, this winter conferences, and then after that you stay 2 years without data. So I think they are pushing quite a lot. As far as I know, we are not exceeding 2 or 3 sigma per experiment, and probably putting together, we cannot have a 5 sigma evidence with the actual data, unless maybe some angular analysis will be further pushed. But I mean, angular analysis is not so simple. So I mean, of course, when you start to see things like that, behaving like standard model, branching fraction, you do preliminary measurement of spin characteristics, and you find that at 2, 3 sigma is compatible with 0 and not with 2, you start to think that you are like slowly moving there. But I would say, I don't know, Maxime, but I think we will not reach 5 sigma now.
No, I think we will not reach 5 sigma now with all the data analysis, but the point is that whenever what Achille was showing at the Higgs to ZZ became to collector. It's all this analysis used on the multivariate technique. And this some of the multivariate technique explicitly assume whenever you select this event, because they come from Monte Carlo generator, that this is spin 0. And the point is that by this technique you're selecting the particle and you really start to see a bump. If it would be spin 2, then you would be basically optimizing much less sensitive to this particle, which is too represented by the So indirectly, it points to the direction of 0, but statistically, 5 sigma.
I mean, Maxime is perfectly right. In fact, I forgot, this is a very important point, that the fact that when you, for the Higgs discovery, the use of angular distribution was an angle to increase the significance of the signal. Now, if you want to have the information on the spin, you have to remove this variable from the analysis. And so is I mean, the signals are not so clean. So you have to find other analysis. So, but I mean, let's say at 2, 3 sigma level, yes, but far from that, I think we need to have more statistics from new run at 14 TeV.
Mainly, I meant parity.
Yeah, no, this is even less, I think. Is even less established. Between plus and minus is even less than that. I think, yeah.
Okay, another question? Может, кто хочет по-русски?
There is plans in the scientific community, maybe fantastic plans to build a large linear collider.
Yes.
Could you comment what will be the correlation with the LHC and the prospects to find new physics there?
Excellent. Yeah. Yeah. I think that, I mean, in fact, I had few transparency, but then I realized that they're a bit, because we okay. First, I answer to your question. In fact, okay, let's say linear collider has a great opportunity to do what? I mean, first of all, you have a linear collider. Okay, I started differently. If you take now LHC and you go to upgrade of LHC with high luminosity, of course, some of this measurement will improve. So you will probably be sure about the spin parity of the Higgs, and it will improve the precision on the branching fraction of the Higgs. And probably you will start to address partially also the coupling of Higgs to top. Okay? Now, which is the characteristic of a linear collider? The linear collider, if you are able to construct a linear collider at 500 GeV, because also this is a question, you can do a linear collider at 250 GeV, 350 GeV, but the best would be 500 GeV. In this case, of course, you will measure the branching fraction at a fantastic level, like less than a percent level, and all the branching fraction, CC bar, tau tau, all the branching fraction. Because in this case, the environment is very clean, you have just the plus and minus collision, very few particles, so it would be really a very precise measurement of the branching fraction. This is one point. Then you have also very precise measurement of a coupling with the top, but of course you need to be at 500 GeV, not below. Then you can start to address the triple X coupling, so you have the X coupling within itself, so X to XX. So this you can study, which is a fundamental
whatever is left in addition to Z boson and Z left. And then it's completely independent. Here, in some of the coupling measurements, it involves new physics in the production and decays. There, you have a precise, this is the only way to measure the total width of the Higgs, and in addition to this, to completely be decoupled from what Higgs decays, you just look for equal mass and then you reconstruct only the Higgs decay modes.
Thank you. Okay. Yeah, so
Please.
So I have a question. So when I think about the Higgs, the two channels, basically gamma gamma and all that,
Yeah.
the question is which channel actually is the bulk of the information?
Yeah, excellent question. I didn't spend much time, but if you, I mean, I have probably not the final result, but here you can look at that. Okay, but this is not the final. Do I have maybe here? Okay, let's say that. Okay, I check if I have the final plot. Right. Okay, so you can see here. Okay, it's not really the final, but you can see here that you can read to answer quantitatively to your question. You can read it here. So in here in green you have gamma gamma, and in red you have ZZ and the others. Okay, so you see that this means okay, it's observed, but you see that both they contribute almost equally. So means that if you used the gamma gamma alone, you would have established the X at 4 sigma level. So what you have seen in gamma gamma is compatible with the background fluctuation at 4 sigma level. And in ZZ is slightly larger than Z sigma level. So the two channels are really leading the final significance. So at the end you say you are at above 4 sigma, and at the end you end up with 6.9 sigma. So when you put the two along the rest, you see they are almost equally contributing.
And what concerns the spin is
now for the spin, I think ZZ is better in some extent because it's more easy for many point of view. I mean, the precision you can let's say the angular distribution you can get much more easily from leptons than from gamma. Okay, gamma direction is good, but I mean it cannot be as good as leptons. So I think at the end the winner for spin will be for leptons, definitely.
Question? Comments?
Announcement?
I would like to say to Professor Achille for nice lectures on CERN data, different results about analysis, and very important that we all know about physics up to 1 TV. Yes?
Yes.
That's okay. Announcement, but perhaps that in Russian. Профессор Achille организовывает в этом году школу для молодых ученых здесь у нас в Харькове. Но она будет проходить не здесь, тут не получается, в Салтове. Это будет в июле месяце для молодых студентов, для молодых научных сотрудников. Ну, где будут даны все лекции, большое число лекций, 10 дней, относительно проблем, в частности, которые затрагивались здесь. И я также хочу поблагодарить профессора Максима Титова и Сергея Барсука за комментарии, которые здесь были, за участие, за обсуждения, которые здесь были. Давайте поблагодарим всех. И мы надеемся, что наши гости будут часто 1 week, and the team Yuri Petrovich Stepanovsky, spinners from Pythagore to Majorana and Penrose. Very interesting team also.